right, we're going to take a look at 1.1 today, mathematical problem solving. Just one moment. All right, now most of what is content, just written content, is already typed on your slides. We're going to use the board to do some other cool things, and I want to show you some things as we go along. Some of the things that I will show you are things that I could have prepared in advance, no doubt. But the point is I want you to see how you get those images on the screen with the smartboard. So some of those things I'm purposely creating inside of this environment that we're in so that you have that experience, okay? All right, all right, so if you take a look, the first thing we're going to be doing today is talking about mathematical problem solving, and there's basically a 4-step problem solving process. I think I only put the first 3 in here because you can consolidate it often into these 3 steps. So maybe I should have called it a 3-step problem solving process, but that's okay. The first step is to understand the problem, and just reading the problem doesn't really accomplish that task. That's certainly the first thing you would do in any kind of a math problem is to read it and make sure you read all the directions and all that kind of stuff. But there's some different questions you can ask yourself. For instance, can the problem be stated differently? What is to be found or what is needed? What are the unknowns? What do I not know? And then also, what is known? What information can be obtained from the problem? That's what is known. And then what information is missing or not needed? So you all remember those problems you had at some point where they gave you some piece of information that you didn't need to do the problem? That happens sometimes. And the reason that you encounter that in a math classroom is because that's what happens in real life. You don't need every bit of information in order to really solve the problem. So that's the kind of things you have to be thinking about contextually in real life. So that will happen sometimes in problems that you're given. Devising a plan, this is where we're going to spend the majority of our time when we get to the examples, is what problem-solving strategies might we use. And there are a lot of problem-solving strategies. I'm not going to give you an example of every one of them, but we're going to examine several of them. Like this says, it's not exhaustive, but it is useful. And so we're going to talk about a few of these. Looking for patterns is one of them, especially if you're predicting the next thing, right? So if I show up late every day next week to class, what do you think is going to happen by the second week of class? Well, you are going to assume that she comes in every day late, right? These are patterns of behavior. You can look for patterns within mathematics as well. Examining related problems to see if the techniques can be applied. So if you already know how to solve this one problem, how do I solve this other one? And you see that in mathematics all the time. That's why there's examples in your textbook for you to go back and look at, right? As you look at it, you say, well, that's kind of like the one I'm working on. How can I do it with that idea? Okay. A simpler or a special case, we're going to do an example of that one. You may or may not have seen that happen before, so we're going to do an example for that one. Tables and lists. I am a list person. I don't know if any of you guys are list people, but I'm the kind of person that has a to-do list, and if I do something that's not on the to-do list, I write it on the to-do list and mark it off. I'm a list person. I like lists. I like organizing things. I'm an organizer. When my daughter was about 2 years old, I know she was either 1 or 2, and like the end of when she was 1 or beginning when she was 2. She was sitting at the kitchen table one day playing with crayons. She wasn't coloring, and I said, "What are you doing?" And she said, "Mama, I'm organizing." And I'm like, "Yeah, she's mine." So this idea of being organized or whatever, this organized learning idea, that's along with this idea of being able to take a table or a list. Identify a sub-goal. Often there are problems that are more like multi-step problems, and there's some sort of intermediate step that you have to get to before you can move on. And if you're just looking at the whole big picture, it can feel a little bit overwhelming, like where do I go first? But identifying a sub-goal kind of breaks it down into smaller tasks. Making a diagram, again, pictures are often helpful, and they'll be exceptionally helpful when you guys are looking at your students, because a lot of people are visual learners, and actually a very visual learner too. I tend to make diagrams and create tables and lists, sometimes all within one problem. And I'll show you some examples of how you can combine these as well. But creating a diagram, and sometimes, and often of course the diagrams you create are not to scale and things like that, so you want to be careful when you're teaching when you tell students that. But diagrams are very helpful. Guess and check is not cheating, and it is a perfectly legitimate way to problem solve, doing a guess and check kind of method. Now, randomly guessing and checking is generally not so good of an idea. But educated guesses, changing what the guess was that you had and it didn't work, and re-guessing in a better way, that's what we mean by guess and check, not just randomly guessing and checking. This is like my son, right? He sits down and when he gets confused about the letter W, because he always gets confused with the letter W, he goes and he says N, I say it's not an N. He says A, B, Q, R. No, guessing's not what we want here. That's not the goal. So random guessing is not what this is talking about. So be careful when you see guess and check when you don't inadvertently think that. Working backwards is one of those that can be very helpful. You guys, I would almost guarantee that everyone who's worked with problem backwards before. And here's the case when you've done it. You've said, I don't know how to do that problem. And you take your textbook and you go to the answer and you back and you say, how'd they get that answer? Right? And then you somehow try to work backwards into the problem that they gave you. My daughter likes to work mazes backwards. They're lots easier backwards. So again, it's the same thing, right? You know, it's easier to do backwards. So there are certain problems that are like that, and we're going to see an example of that one as well. Writing equations is probably one that you're very familiar with. I'm not going to do an example of that one because you've seen that plenty. You've seen that all over algebra. There are cases when writing an equation is a great way to do it, but the kids that you're working with aren't going to see that as much. Now, they do see things that look like equations, they just don't have the variable notation in them. So occasionally you'll see something written, and it comes in with my kids' papers too, where it says something like 14 minus blank equals 12, and they have to fill it in. That's an equation, right? And so there are equations that occur. Don't think that just because you're working with elementary kids, you're never going to see equations. They're just not going to look like the algebra equations that you're accustomed to as a kid. Okay? So these are some different, not exhaustive, but different problem-solving strategies that we're going to take a look at. The last thing to do after you have solved the problem, or you've identified how to solve the problem, is to actually do it. Carry out the plan. So carrying out the plan means implementing the strategies from step 2, performing necessary actions and computations. It says attend to precision and language mathematics used. So there are some things that you write down a solution. For instance, you want to make sure that you use units. You know, 3 feet is different than 3 meters, that kind of stuff. So be careful about your language that you're using in your work. Checking each step along the way has to be formal or intuitive. So formal means you actually, for instance, if you were working an equation, you actually plug the numbers back into the equation and make sure it works. That's a formal way. Intuitively means looking at it and asking yourself, does it make sense? A lot of times kids don't do that. You guys probably have not always done that either, right? And so I give a test and somebody's solving some equation and they tell me that there are 14.32 termites. Well, there can't be 0.3 termites. That doesn't make sense. So that's the intuitive kind of checking your answers that I was talking about. And then keeping an accurate record of your work. So scratch paper is great, but make sure that you actually keep it until you're done with the problem, that you've got all of it transferred on however you solved it there with you. And the last step, step 4, that you're not seeing over here is actually checking your final solution. And the reason I said you can kind of wrap that up into step 3 is because if you're checking every step along the way, then you've kind of already done that. Make sense? Okay. We're going to look at one, and this may be the only one we get to today. We won't have homework assigned, so everybody can pre-decide. If your goal over the weekend is to make sure that you can actually access individual rooms, there's nothing out there for you to print yet. And in fact, you don't need to anyway, because we won't do 1.2 until Wednesday. But make sure that you can get in there and do more keywords and everything, okay? But this is the lesson we'll finish up on Monday. So the first one we're going to talk about is looking for a pattern. This is an interesting problem, and it's actually the exact problem inside of your book, which I don't normally do that, but it's historical, really did kind of happen kind of thing, so I think it's important for you to realize, and it is interesting. Gauss was a mathematician, and in grade school, and I don't know exactly what grade, but I'm thinking it was probably 3rd, 4th grade. Gauss's teacher decided that she wanted to give the kids some busy work, more or less, right? She needed to get something done, so she told them she wanted them to add up the numbers from 1 to 100. And that should take them a good little bit of time, right? Well, Gauss was a very intelligent person, and he saw patterns. That's how he thought. And so this is what he did. So the first thing we're going to do is we're going to kind of write this out. And I'm going to write out kind of what he was told to do. He was told to add 1 plus 2 plus 3, and to keep adding until he got to 100. Obviously, if you add all this up, it should take you quite a bit of time. Agree? Yeah, I mean, there's no reason that, and there are no calculators allowed here, right? So Gauss was a pre-calculator. And this should take a child quite a long time to do it. But it didn't take Gauss a long time to do it. And this is what he did. He did this, or he noticed this pattern. So I'm going to draw my curves for it. All right, so what is 1 plus 100? 101, right? Sure. What is 2 plus 99? There's 100 of those, aren't there? 101. 3 plus 98? 101. Do you notice a pattern? Yeah. So if you pair them together, they all add up to 101. And you can keep working your way inward and do this. And this is not specific to the numbers 1 to 100, right? You could generalize this, in fact we'll go on our next example next time, to do it with any set of numbers. Now that didn't answer a question yet, right? I mean, I just have noticed the pattern. How do we use that pattern? Well, so what we're going to do is we're going to take each of these and I'm going to replace every single one of them with the number 101. So bear with me so you can see what's going to happen when we do that. So my 1 turns into 101, my 2 turns into 101, my 3 turns into 101, and then I've got the last 3 also turning into 101. Obviously this is more than I had before. How much more? Twice as much, right? Because 1 and 100, these two added up to 101. I've replaced each of them now with the number 101. That's exactly twice as much as I had before. So we're going to use some notation. Gauss probably didn't use our notation. Basically, we doubled what our sum S was. Now here's my speculation is Gauss had to have done a little bit of multiplication in order to continue this process because, yeah, adding up the numbers 1 to 100 is one thing, but I mean, you just replace it with adding up the numbers 101 a whole bunch of times. That starts to sound an awful like multiplication to me. This multiplication is what we call repeated addition, right? At some point, a child says, I don't want to add 2 plus 2 plus 2 plus 2 plus 2, right? I just want to do 2 times 5, okay? So the question becomes, how many of these guys are there? How many 101s would I have written if I had actually written them all out? More. Because how many numbers are there from 1 to 100? There's 100. Now that's really nice and clean here because I see the number 1 and I see the number 100. Well, I'll show you what happens when you don't have it. Like on the next slide, I think it's starting at like 37 and ended up at 146 or something, whatever. But for this one, you can pretty quickly see that there's 100 numbers from 1 to 100, right? So this is actually 101 100 times. Okay? So I'm getting this because there are 100 numbers from 1 to 100. And that's what's happening. So how am I going to solve for the sum? Because if I do 100 times 101 now, which you should be able to do pretty quickly, that's still not exactly the number I want, right? How do I find the sum that I wanted instead of twice the sum? Divide by 2. So that's what Gauss would have done. He would have actually written 2s equals like I just wrote, but the idea is the same, okay? So we would divide this by 2. Okay, so here's the first smartboard trick besides using the, essentially like whiteboard markers. I can press this extend the page and it gives me more space, which makes this a lot better of a program in some sense than like a PowerPoint slide. You don't have that kind of ability. By the way, I didn't say this, but the program I'm using is called Smart Notebook. It's something that you can put onto your own computer. Google Smart Notebook. If there's a cost associated with it, I know the Ed department will provide you with whatever code or whatever it is. You get it as a part of the packaging. But I think, I could be wrong, but I think it's free anyway. I don't think it's something that you go out online and there's a charge for it, but I could be wrong on that. So it's something you're going to want because you're going to be using it more than just this class. Anyway. All right, so let's finish this. All right, so if you decide to do this, you have a couple choices. You can either divide this right now, or you can multiply these two and then divide. It doesn't much matter. But I'm going to divide this out now. So if I take 50 times 101, or if I take 101 times 100 divided by 2, what do I get? ideas in it, properly, but yeah, 5,015 would be the sum. And that was Gauss in maybe about 3rd grade. So, right, he's a mathematician, obviously well known because I can tell you his name. The deal was, though, he noticed a pattern. And we can use patterns often to solve, and he wouldn't have made it look like this, right? We can use patterns to solve things that otherwise would have been very cumbersome to work with. Even with a calculator, I don't want to add 1 all the way up to 100 together. It still would take me a long time to do. So this is Gauss. Just a sec.